So in this video, we are going to discuss equilibrium, a reversible equilibrium process, okay, with regards to proteins and small molecules. And so at equilibrium, we have A plus B. They're separate and distinct species, but then they can come together. And what we're going to do is, instead of looking at this equation in that way, we're going to look at it in terms of proteins. So P for protein plus the L for a ligand. And when you have a protein and a small molecule that we call a ligand, and when they bind and associate to one another, it looks like this. Okay. And within P, or the protein, there's going to be a site where the ligand goes. The ligand doesn't go to everywhere on the protein. So if we have like a protein like this, the ligand doesn't bind here, here, or here, or here. There's typically one spot. And that's not very good, is it? We'll just go like this. Typically, there's just one spot where the ligand goes, and that's called the binding site. So we're going to take a look at this interaction. And this interaction has to be reversible. Okay? And in this discussion, we're going to look at how these ligands bind to the protein, and then how those ligands are released from the protein. And this right here is a much better representation of that. So the equation, let's rewrite it over here. It's P, protein, ligand, equilibrium process, like that. So that's what you see on that slide right there. And so what we have here is pay very close attention. Oh, what is that there? There we go. Got to show the whole slide. We have to pay very close attention to these constants. And there's going to be like 4 of them with the letter K. But pay attention. This is a lowercase k right there. And these are the rate constants associated with kinetics. So Ka is saying in this direction, going in the forward direction, how fast does the ligand, represented by this triangle, associate with the protein? And then lowercase kd right here, sub d, that's the dissociation, which means how fast does this complex of this protein and the ligand, how fast does it dissociate and fall apart into these, the separate individual pieces? So those, the lowercase k's mean kinetics. Okay. Now, at equilibrium, when it reaches equilibrium, this is now true. That the association rate and the dissociation rate now aren't changing. Okay? They're equal. And that's what happens when we come to equilibrium. Right? Now we have capital K and capital K right there. Capital K is looking at equilibrium. Okay? And the Ka, this little a right there, represents the association. And we have to be very careful because in general chemistry, we had Ka, and that was the dissociation constant of the acid. And that told us how acidic an acid was. Larger the Ka, more acidic. But that Ka in reference to acid strength is not the same thing as this capital A, or capital K sub A. This is the equilibrium constant for the association of the protein and the ligand. Okay? And then you can see the relationship that Ka is inversely related to Kd. And capital K sub D simply means, what is the dissociation? That's the dissociation constant. So we're going to look at myoglobin and hemoglobin and look at those proteins to kind of understand this process and why it's so important to understand. So let's continue on. So if we take a look at Ka a little bit more closely, okay, we see it right here. We see that the Ka is what? Products divided by the reactants, just like any other equilibrium constant that you've seen in the past. It's the same idea. And so I don't want you guys to get too caught up in the math on this slide. The next video that you're going to watch, I'm going to go through the math in detail. So what you need to be aware of on this slide is this is the definition of Ka. That's a very, very important bit of information. Okay. And the PowerPoints, there's like a typo in them, okay? This theta symbol right here, it's not a theta when you go to your textbook and read it. It's actually a capital Y. So in this video, if I show a equation and there's a theta, get rid of it and replace it with a Y. Like that. Like I said, don't worry too much about the math. You'll learn more about that in the second videos. Okay. But we have to understand that Ka is the association of the protein and the ligand, and Kd is the dissociation constant. So if we have a protein binding to a ligand, or a ligand binding to a protein, what we have is that we can run an experiment in which we track and we graph the Y with respect to the ligands, the concentrations of the ligand. And what this is showing us is how well does the ligand bind to the protein. So if you have all these proteins, you have to add X amount of ligand in order for it to bind. Oftentimes it's not, oh, there's one protein, one ligand, it's going to bind. It's going to be more like, oh, there's a few proteins and tens of thousands of ligands, and not all those ligands are going to bind to the protein. So you're going to have a mixture at equilibrium of some, that's missing a triangle right there. So there's our ligand. So at equilibrium, we're going to get a mixture of protein and the ligand bound, and then it's separated. So we're going to have a ratio of this and that. And so what we could say is this side over here is unoccupied. So unoccupied. Goodness. versus occupied. Okay. So we have that ratio. And that's what this Y term in the graph is representing. The ratio of this to that. And so on the x-axis, what we're tracking is how much of the ligand do you have to add in order to get this ligand to bind in the binding site. And so that's what is so important about this value right here called KD. The definition of KD is when we have 0.5, when Y equals 0.5. That simply means that half of the binding sites that are available are bound. So it's a 50-50. We have half of the ligand bound to the protein and then half of the proteins with no ligands. They're unoccupied. And so when we run the experiment, we'll see this hyperbolic curve. And so once we look at the y-axis, we can extrapolate down, and that's going to be the KD, which is the dissociation constant. And with dissociation constants, we can have different well, let's look at it this way. Well, let's answer the question, well, how do we interpret the value of a KD? So a KD, that is, or a interaction right here, this interaction, if that interaction is very, very strong, where the ligand wants to go there and stay there, if that's a strong interaction, then you don't need a lot of ligand. And so a strong binding corresponds to a very, very small number. Smaller amount of the ligand that you have to add to get to 50% occupation is a small value, a small number. But if the ligand doesn't bind very well, it's going to take more and more and more ligand to eventually get to 50%. And so that's what you see here. When you have a weak binding right there, you have a much higher concentration. So we are comparing, look at that. It's not comparing 10 to 10, it's comparing 10 nanomolar to 10 micromolar. That's 1,000 units difference, 1,000 times difference. Okay? So the way that you want to interpret KD is smaller the number, better the binding, the better interaction that you have. So if we look at it graphically, okay, let's do a red one. If I draw another curve, something like that, where is its KD? Well, we do the same thing. We extrapolate from 0.5 and then go down. So this is the KD for this imaginary protein. So which one binds its ligand the best? All right. Coming back to this, a smaller KD means tighter binding. So the black curve has a smaller KD. So it binds much better. So we can interpret this as something maybe, let's use these numbers. So this KD is 10 nanomolar. That's the concentration of the ligand at this point. And if you add 10 nanomolar, you get 50% binding. But this guy, this one right here, let's say is 10 micromolar. Okay. Now, my units here on the x-axis aren't accurate, right? So I'm just making this up as we go, but so that is that's more concentrated. It took more ligand to get to 50% binding. So it doesn't bind as well. So that's how we interpret this graph or this data. All right. So here's some examples that you guys can go investigate and look into. Okay, we have biotin right here. Look, very, very small KD, so high binding affinity. We're having enzymes and substrates bind with low affinity. These numbers are larger than those numbers. So this is just an example of the varying types of proteins or interactions that we are going to study. And so I'm just hoping that you guys can grasp the concept. Small KD means strong binding, large KD means weak binding. All right. I now want to take a look at this binding of the ligand and the protein. So take a look at it a little bit more closely. And how does this ligand bind to that spot? And more often than not, the ligands and the binding sites, they're compatible. And they're very selective, that only this type of ligand can go into this binding site. That's typically how it works. Now, there's exceptions to that, but a very specific enzyme is going to target one or a few ligands, and that's it. And so in order to understand how it can be so specific for a particular ligand, we got to understand some of the models and theories that help us explain that specificity. All right, so we have some specificities, and we're going to take a first look at the lock and key model. All right. Now, how does the ligand bind to the protein? Well, there's many ways in which it can be complementary to the protein, and that is based off of the size of the molecule. The shape is huge. I've talked a lot about the shape of molecules and why that's so important. We can look at different charge states of molecules, and then you have hydrophobic or hydrophilic ligands and binding into the binding site based off of hydrophobicity. So the lock and key model, okay, shows this picture down here below. Let's say this guy's the protein and this guy's the ligand. And in this particular model, it kind of is representing shape, okay, like size and shape right here. You can clearly see that, hey, that shape right there, that is the binding site. And on the ligand, we have this nice little curvature right there that fits nice and snug. So that's our protein, that's our ligand. And so in this lock and key model, the binding site and the ligand already have the shape where it's like a hand going inside of a glove. It just fits perfectly. And the shapes of every component there is just what they need to be. And so when those two shapes come in contact with another, it just makes sense. Hand goes in glove. It fits perfectly, right? Because if we had a different type of ligand floating around in this mixture, let's say a square, clearly that square can't fit into the binding site due to its shape. So that's why this protein is selective for this ligand and this ligand only, and not this other black molecule here, or other ligand. Okay, so that's the first model that helps explain the specificity of ligands and proteins. The next one is called the induced fit. Is this even changing on me? No, it's not. I tried to change something, but it didn't work. Okay, the next model to explain binding is an induced fit model. Now, this model says that the induced fit allows for a tighter binding, okay, and much higher affinity than the lock and key model. And that happens to be because we have a protein and a ligand. And clearly this ligand, okay, can fit in that space. Not a perfect fit, but it can actually get in there. That end could get in that space, or even that end could get in that space, or maybe even this edge right here. It doesn't matter, okay? It's just the fact that this can fit into that binding site. And then once it gets close enough into that binding site, the proteins change their conformation. So this is the same protein over here. It's just once a ligand starts to go into that binding site, the protein changes shape to bind more tightly to the ligand. Sometimes the ligand shape doesn't change. It just stays the ligand. But in this example here, we see that the ligand also changes. So you can have multiple combinations here in which the protein is the one that changes its shape when the ligand gets bound and then fits with the ligand much more tightly. Or you can have a situation where the protein and the ligand change conformation so that they fit more tightly. And so you see that connection right there, nice and tight. And that's called the induced fit model. So now I want to start getting into a particular set of proteins that help us understand more deeply this picture right here. So I want to get away from, oh, here's a shape, here's a triangle, they fit together type thing. Let's look at some real life examples here. That's where I want to get to, okay? Now, let's set up the problem. So we know that we need oxygen to survive. We know we need to get oxygen in our bloodstream so it can go to our extremities and give oxygen to our muscles and our organs and everything that needs it. And it travels through the bloodstream. However, we learn from general chemistry that oxygen gas is not very soluble in water, let alone blood. And so that's going to be a problem. If we can't keep oxygen in the bloodstream, how will it get to where it needs to go? Okay, so that's the problem. How do we transport oxygen in our blood when it's so insoluble? One solution could be maybe we could get oxygen to bind to proteins. Because there's proteins in blood, could the proteins carry the oxygen? And the side chains of proteins can't grab onto oxygen very well. It doesn't do that. So maybe we could use some kind of metal We've heard of iron, and we know iron is in blood, but if it's just free iron in the bloodstream, then that's going to mess with oxygen and convert oxygen into a free radical. So if you go into the lab, take iron and oxygen, put it together, you're going to form radicals. And oxygen radicals, very, very bad for your health because they're so reactive. And they're going to cause DNA damage and just damage to really anything that it comes in contact with because they're so reactive. And so, a little side note, that's why we like to eat antioxidants, so it can go after these oxygen radicals. Because unfortunately, there's no way around not forming some oxygen radicals in our systems because we're constantly breathing it in. Okay? But we want to limit that. Limit the amount of oxygen radicals. So just oxygen and an iron molecule floating through the bloodstream, no good. Because remember, what's the problem? The solubility of oxygen gas in the blood. So we're trying to think of ideas. Take oxygen, put it on a protein to make the oxygen stay in the blood. That won't work. We're thinking maybe take metal, attach oxygen to metal, and keeps that in the blood. But that doesn't work because it turns oxygen into a radical. Okay, so the best way to do this is have iron in a structure like this that makes the iron still be able to bind oxygen, but is less reactive when it's just all by itself. So when it's in this molecule here, this iron atom is in the center of that molecule there, it reduces the iron's reactivity. Okay. So let's see here. But what's interesting is that this molecule here is called heme. If you take oxygen and attach it to the iron molecule in heme and heme only, it's still too reactive. Okay. Still not very good, because what would happen is if you have just free heme all by itself with iron in there and you attach oxygen to it, it's going to oxidize this iron atom from a iron 2+, so ferrous, to Fe3 ferric. And when you have iron in the ferric state, it does not bind oxygen. So now we just basically came back to our problem that, hey, we can't get oxygen to stick to this heme molecule when iron is F or iron 3 or in its ferric state. So we have to come up with another solution, and we didn't have to come up with it. Biology did it, right? And that's the cool thing, is that there's some proteins called globins. Myoglobin, no, globins. Misspoke. So we have globins right here. Now, I don't know why I cannot get this to shrink down. That's a little frustrating. No. So let's look at these globins right here. Okay. So what happens, biology is like, well, let's take heme, which is shown with the red molecule. This orange sphere, that's our iron 2. And we'll take that heme and stick it into a protein called myoglobin. And myoglobin is a protein that now can bind oxygen and store it in the muscles. so it can transport oxygen. Well, myoglobin stores oxygen in muscle tissue, typically found in animals or mammals that are in the ocean, so like dolphins and whales. So when they go into their deep dive, they still have oxygen stored up in their muscles, but that oxygen is going to be bound to myoglobin. Hemoglobin is the globin protein that transfers oxygen through the bloodstream. Now, what we're going to do first is take a look at myoglobin because it's more simple. It's just composed of these 8 alpha helices right here shown, and we label those alpha helices A through H. And so there's 8 alpha helices in the center there. We have our heme. Okay. And what we're going to find is that we have histidine 93. So the 93 tells us where the histidine is in the primary sequence. But we could also refer to histidine 93 with this his for histidine F8. And what that means is the histidine is going to be found in the F alpha helix at position 8 in that alpha helix. Okay, so there's 2 ways to refer to it. And that histidine is really, really important in how it interacts with the heme. And then we have this histidine right here. This is called a distal histidine. We'll talk more about that in a moment. But that's also going to come up in our discussion as well. So we're highlighting those. Okay, and then you see this term right here, CD, and that's pointing to that structure right there. So that loop that connects the C alpha helix and the D alpha helix, we call that the CD loop because it's connecting those 2 alpha helices. Okay. So before we go any further, I want to go over some definitions. And here's the 3 words that I want you guys to understand and differentiate between one another. And we'll look at these one at a time. Okay, we already talked about ligand, but let's just go through it again just to make sure we have it, okay? So it's really important to understand that it's a non-covalent interaction between the protein and the ligand. Okay? And once again, my ligand here has disappeared. So that has to be in there. Now these ligands, they can be ions, small molecules like oxygen. They can even be other small proteins. Okay, so when we have something relatively small in comparison to the protein that binds into a binding site, we can call that a ligand. Now, a prosthetic group, okay, is a non-polypeptide component that's tightly and permanently bound to a protein. So, for example, myoglobin. What we have that's tightly bound to the protein is the heme, our heme molecule right there. So non-peptide, so like organic molecules that are bound in a protein. And so the heme molecule is bound and it's interacting in such a way as to keep the heme there. And we're going to delve into how that happens and why that's so important. Okay. So a prosthetic group, something that's not protein, that is in a protein to help serve a function. Now, ligands and substrate, depending on who's talking, what book you're reading, can take those two terms, ligands and substrate, and use them interchangeably. Okay? But there is a distinction. Okay? So a substrate is when you have a molecule that goes to an enzyme. Now, if we come here, that's a protein, and an enzyme is a protein. But the way the protein interacts with the ligand is different. So you see here in a protein, when it binds a ligand, ligand binds, the ligand stays the same. Okay? Triangle, triangle. So the ligand is just binding to the protein to be transported typically, but not to have a chemical reaction done on it. Whereas an enzyme, a substrate, which some people call a ligand, well, that's not entirely true. The substrate will bind to the protein / enzyme and then undergo a reaction. So you can see substrate starting material turns into products, and it looks different. So enzymes will take substrates and do a reaction upon them to turn them into something else. So that's the distinction between a substrate and a ligand. Because in, like, let's say in hemoglobin or myoglobin, oxygen binds to the iron in heme. It stays oxygen. And then in hemoglobin, when it gets to the, let's say, the tissue, peripheral tissue, it releases the oxygen. So it was oxygen before and oxygen after binding. So let's take a look at the structure of heme and break it down into its components. Okay. So let's look at figure A right here. Figure A, this is called a porphyrin ring. So that is a porphyrin ring. And notice that we have all these X's. And so those X's are not saying halogens. It's actually a variable, saying that the stuff attached to the porphyrin can be different based off of species. Once we tack on the X in this particular example here, okay, we want to take a look at this guy in the middle, and that's called oh goodness, this pen. Protoporphyrin 9. So that structure in the middle, we have protoporphyrin 9. And that's the one that we want to focus on when we are talking about hemoglobin and myoglobin in the future. Okay, now in heme, I want you to focus in right here. All right. Now heme is going to hold on to the iron 2 by 4 coordination bonds. And those 4 coordination bonds are from the nitrogen atoms. These nitrogens right here, you can see them right here. All right, and you see that those pink arrows are pointing to the iron. So there's a coordinated bond that's interacting with the lone pairs on those nitrogens to the iron. So if we take a look at this image right here on D, these corners right here, those are the nitrogen atoms. So those 4 nitrogens are keeping that iron in place. But then we have these right here. We have two more unoccupied spots or coordination bonds. Unoccupied coordination bonds. We'll just say uncoordinated spots. It would be that guy and that guy. But this image right here doesn't do it justice. It's that those coordinated bonds are perpendicular to the 4. So that's what you see right here. We kind of get that iron in a plane, and we have the 4 coordinated bonds from the nitrogens, but then we have 2 more spots, one above and one directly below. And that's what we're representing with that image here. So I mentioned earlier that we can't just have heme carry oxygen around because the iron is still too reactive. We need the heme inside of a protein to make it functional so we don't die. Okay? But before we get into how it's bound in the protein, I want to take a moment to show you what would happen if we just had free heme in the blood, what that would do to us. So I'm going to take that heme molecule right here in this plane, or this guy, and I want to rotate it 90 degrees. So we're going to look at it from a side view. And when we look at it from a side view, I'm going to represent it like this. Okay, so we have the iron that's being coordinated. Okay, so this is part of the heme right there, or the porphyrin ring. What happens if we had just heme, no protein? What would happen is oxygen would come around. It's like, oh, that's iron 2 plus. Oxygen combined to iron. But we are going to have a second free heme molecule that's going to associate and kind of sandwich oxygen in between 2 heme molecules. And so when that does that, it's going to oxidize the iron from the ferrous state which is the 2 plus, which is the state that iron needs to be in order to bind oxygen. But with just free heme floating around, oxygen is going to be sandwiched between 2 hemes, and that's going to oxidize the iron. And that's going to give us the ferric. The ferric state, which is iron 3 plus. And in the iron 3 plus or the ferric state, it does not bind oxygen. Okay. Another cool feature about the iron 2 is that in the ferrous state, oxygen binds reversibly. So it can bind to iron and fall off of iron. Iron 3, we don't get any of that. Right? So in regards to hemoglobin, we want a system that will bind oxygen, but then release it when and where it needs to be released. And so these proteins help to make that happen. And I think that's so cool. Let's see what's next here. So in order to make the iron less reactive. We stick it into heme. Even in heme, it's too reactive, so we have to stick it into a protein. And we're going to take a look at sticking heme into myoglobin. And so what happens is histidine 93 right here is going to take up one of the two empty coordination spots. So in heme, we have iron that's coordinated to the 4 nitrogens. And then what happens is when you put heme into myoglobin, histidine 93 is going to coordinate from one face, or represented right here. So it's going to take the nitrogen in histidine and coordinate with the iron. So that leaves one face open to oxygen. And it's going to come on the other side. And oxygen is going to bind to the iron. And now that can be transported or stored where it needs to be until it's needed, and then it can be released. And so it's because heme is in myoglobin and this histidine right here takes up the 5th coordination spot and leaves the 6th coordination spot for the oxygen. That interaction right there makes iron just the perfect reactivity needed in order to bind oxygen and to release oxygen when it's needed to, and to not oxidize iron 2 into its ferric state, or the F iron 3. So I think that's really cool that this protein does that, and we'll talk more about it during class, and we'll start talking about hemoglobin as well. So that's where we'll end this video for now.